All right, today, integration using linear partial fraction decomposition. So we're going to use this method when we're trying to integrate a rational function whose denominator factors into linear factors. So here we go. So check out problem number one here. So when you see something like this, we're trying to anti-differentiate. The first thought you should have is maybe I can do a u substitution. So if I let u equal the denominator, then my du is going to be 2x minus 2 dx. Now, if I had 2x minus 2 or a multiple of 2x minus 2 in the numerator, I could do a u substitution, but I don't have that. So we're going to do something different. We're going to do what is known as partial fraction decomposition. Now, if you took a pre-calculus course, you would have done this. And they probably didn't even tell you why you were doing it. I'm going to show you why you were doing it. It's because it allows us to do integrals of functions we wouldn't be able to otherwise. So what I want you to notice here is that 5x minus 3 over x squared minus 2x minus 3 is equivalent to 5x minus 3 over, I'm going to factor the denominator, x minus 3, x plus 1, right? Yeah, that looks right. Okay. Now, what partial fraction decomposition is it is effectively the opposite of finding a common denominator. What I'm going to do is I'm going to attempt to find two fractions, one whose denominator is x minus 3 and one whose denominator is x plus 1, that when added together will give me the fraction I'm talking about. Now, I don't know what the numerators are, so I'm going to denote them with letters capital A and capital B. And if you've done this before, this will look familiar to you. So my goal now is to figure out what are the A and the B that satisfy this equation. So take this right here. I'm going to multiply through by the common denominator of x minus 3, x plus 1. Now, when I do that here, I'm just going to be left with 5x minus 3 on the left-hand side. On the right-hand side, when I multiply to the first term, the x minus 3's are going to cancel, and I'm going to be left with a times x plus 1. And when I do the last term here, the x plus 1's will cancel. I'll be left with b and x minus 3. So now I have an equation that I can use to solve for a and b. And the easiest way to do this is to do some substitution value. So notice, if I were to let x be equal to negative 1, then this equation right here will be negative 5 minus 3 is equal to, now I chose negative 1 here because I knew by substituting in negative 1, it would get rid of this entire term. So all I'm left with now is b times negative 4. So that's going to allow me to solve for b, and I think in this case, b is going to be 2. Similarly, if I choose x to be equal to 3, I should be able to find the value for a. So when x is equal to 3, I'm going to have 15 minus 3, which is 12 on the left-hand side. And I'm going to have a times 4, and the b term will go away. That's going to allow me to conclude that a is equal to 3. All right, now what does this mean? It means that if I put 3 in for a here, 2 in for b here, I will have decomposed my original fraction into the sum of two other fractions. In other words, this integral right here that I have is now going to be exactly the same as a over x minus 3 plus b over x plus 1. And this is better because whenever you are integrating and you have x to the first power in the denominator, you have a natural log function. So the first term is going to anti-differentiate into 3 ln absolute value x minus 3. Second term into 2 ln absolute value x plus 1. So what I'm doing there is I'm using the fact that when you have x to the first power in the denominator, your output is a natural log. Now, this is an acceptable way to leave it. However, if this were a multiple choice question, they're going to do some things here. Here's what they would probably do. They would bring the initial coefficients up into the log as an exponent. That's that idea where you can, bring up the power like so. So I'd have that one, and then this one would be ln x plus 1 squared. Why did I put dx there? I meant to put plus c. That's funny. Plus c. And then I can do even one more step, which is the sum of logs is the log of the product. So any of these forms here is an acceptable answer. If it were a multiple choice question, they're probably going to write it this way, though. All right, now, if you look up here, first bullet point, if the rational function is improper, divide first. That's what we're looking at here. So improper when dealing with rational functions means the degree of the numerator is equal to or greater than the degree of the denominator. So I have to perform a long division first. So I'm going to, wow, that was interesting. I'm going to divide x squared minus 1 into x squared. 1 times x squared gives me x squared. Subtract, 1 times x squared minus 1 gives me x squared minus 1. Subtract by addition of the opposite, and I end up with a remainder of 1. So what does that tell me? It tells me that my integral, that integral right there, is really the same as 1, which is my quotient, plus my remainder of 1, that's this down here, back over the original divisor. So this, of course, well, the antiderivative of 1 is x, and now I need to antidifferentiate 1 over x squared minus 1. Now, if this were 1 over x squared plus 1, that's inverse tangent. But this is 1 over x squared minus 1. I can't do a u substitution. I don't recognize the integral or the derivative formula, but note that I can factor the denominator into linear factors. So I'm going to have to do partial fractions again. So I'm going to go off to the side here and say, okay, 1 over x plus 1, x minus 1. Let me be consistent there. 1 over x minus 1, x plus 1 is going to decompose into sum a over x minus 1 plus sum b over x plus 1. Multiply through by the common denominator. I'm going to end up with the equation 1 is equal to a times x plus 1 plus b times x minus 1. And by careful selection of x values, let's say I let x equal to 1, then I get the equation 1 equals a times 2, or a is 1/2. And if I let x equal to negative 1, that will cancel out the a here. I'll end up with 1 is equal to b times negative 2, or b is negative 1/2. So come back over to my result here. I've got the x in front already, which was an antiderivative of 1. And now my second integral, I'm going to rewrite the integrand, the inside, as a over x minus 1. So that's a half over x minus 1. And then b over x plus 1, like so. And once again, I have a constant on top, a linear term in the denominator. So my antiderivatives are going to be natural logs. So I've got the x in front. I've got a 1/2 ln absolute value x minus 1. And then I've got a minus 1/2 ln absolute value x plus 1. Now let's do this rewriting again. So bring the 1/2 up. Now when you bring the 1/2 up, you can write a half power as a square root. And I'm going to do that. And the benefit of that is I get to drop the absolute value because square roots are always positive anyway. So I don't even have to worry about that. And then minus ln square root x plus 1. I almost forgot my plus c. And then my final step is I can combine these two like I did above, but now it's a subtraction. So when you combine the difference of logs, you get the log of the quotient. So x plus ln x minus 1 over x plus 1, square root of that whole thing plus c. So I could have left it as radical x minus 1 over radical x plus 1, but you can combine it all as 1. All right. And then let's look at one more here. This is a definite integral. So I'm going to do my partial fraction decomposition, and then I'm going to have to apply the limits. So let's do the partial fraction decomposition first because it's already factored for me. So if we look at this, 3 over x minus 1 times x plus 2 is going to be equal to sum a over x minus 1 plus sum b over x plus 2. So we need to find the a and the b. So I'm going to multiply through by that common denominator of x minus 1, x plus 2. 3 is a times x plus 2 plus b times x minus 1. All right, let's let x equal to 1. That will say 3 is a times 3, or a is 1. And then if I let x equal to negative 2 to cancel out this term, I'm going to have 3 is b times negative 3, or b is negative 1. All right, so my integral from 2 to 3 of 3 over x minus 1 times x plus 2 is exactly the same as the integral from 2 to 3 of a over x minus 1 plus b over x plus 2. And once again, these are each going to be natural logs. So ln x minus 1 minus ln absolute value x plus 2. Don't need the plus c this time because it is a definite integral. So that's from 2 to 3. And then I'm just going to go ahead and combine these right now. This is equivalent to ln of x minus 1 over x plus 2 in absolute value from 2 to 3. So once again, difference in the logs, log of the quotient. And now let's finish this by substituting in the values. ln, so when I plug in 3, I'm going to get 2 over 5 minus ln of 1 over 4. So ln of 2/5 minus ln of 1/4. I could leave it like that, or I can combine them. This is the same as ln of 2/5 over 1/4, which is the same as the ln of 8/5.